Chapter 1: Sound, Waves, and Vibration. We are constantly surrounded by sound. We even have a highly specialized opening in our heads for making sounds that may be meaningful to other people. We communicate through sound. In fact, it is our major means of communication. When we disturb the air in any way, we create sound. The slightest motion of our bodies disturbs the air around us and we produce sound. When we raise our hand, we compress the air in its way, and that compressed air front will travel away from us at the speed of sound, which in air is about 740 miles per hour. When we make periodic movements with our hand, the sound becomes a note. By sound, we mean hear any random acoustical disturbance that may be composed of many different frequencies. A note, on the other hand, is a sound of single frequency. We call this kind of sound infrasound, that is, sound below our level of perception. However, when a fly or a mosquito beats its wings, it does it fast enough, and we sure can hear it. The rapid flapping of its wings produces evenly spaced compressions and rarefactions of the air that becomes audible to us. In short, a fly or a mosquito is producing a sound or a note. Let us try to make sound in a less obvious way. We shall take a short piece of wire, connect both ends to a battery through a switch as in figure 1, and close the switch. We were told in school that three things happen. Number 1, that electric current will run through one side of the battery to the other. Number 2, that a magnetic field perpendicular to the current will shoot out and expand all the way to infinity at the velocity of light, which is about 186,000 miles per second. And number 3, that the wire will heat up slightly. They probably did not tell us, number 4, that when the wire heats up, it expands, and by so doing, it will clearly force the air out of its way and make a kind of sound. Or number 5, that as the mass of the wire is accelerated in this way, it will produce gravitational waves. Since any time a mass is accelerated, it will broadcast gravitational waves, which will again expand to infinity at this velocity of light. Some will say that the gravitational waves will certainly be almost infinitesimally weak, but that does not worry us as long as they are there. So our action of closing the switch has been broadcast, theoretically at least, to the outer limits of the atmosphere around the Earth due to the movement of the air, and was broadcast all the way to the end of the universe by expansion of the magnetic field around the wire and by the gravitational wave due to the wire's acceleration. The purpose of this example is to show how, in principle, even our smallest, most insignificant actions will be broadcast far and wide and thus influence something or someone, whether that something or someone is aware of it or not. We should look now at other effects of sound. If we stretch a string on a frame, as in figure 2a, then pluck the string in the middle of the length, we shall see the outline of the string in the extreme positions of its movement. It forms two symmetrical arcs as shown. If we pluck the string at 1/4 mark of its length, we shall see a shape as in figure B. These are standing waves. We get such waves only when plucking the string at distances that will divide the string into integral numbers. Figure 2a shows the frame length corresponds to a half a wave, while in figure 2b, the frame accommodates a full wavelength. In figure 2b, the string has a point in the middle at which the string is at rest, and two more points at which it is attached to the frame. Such points of rest are called nodes. All the other points of the string are vibrating up and down. When the nodes along the string appear stationary and fixed while the rest of the string is vibrating, we call such a behavior a standing wave. Suppose we now take a thin sheet of metal, as in figure 3, clamp it at one edge so that it stays in a horizontal position, spread some dry sand evenly over the sheet, then take a violin bow and draw it over one of the free edges of the sheet until it emits a note. Very soon we shall see that the sand grains are collecting on the sheet in a symmetrical pattern. As we apply the bow at different points along the edge of the metal, we shall get different and quite beautiful patterns on the sheet. The reason for this aggregation of sand grains is that we are setting up the so-called standing waves in the metal. These standing waves in the metal sheet are two-dimensional version of the standing wave on the string. These standing waves have active areas where vibration that vibrate up and down, and other areas or nodes that are quiescent. The sand grains will move away from the vibrating areas and accumulate in the quiescent areas. The sand grains like to be left in peace, and they will go to the quiet, low energy places. This pattern in sand journal actually outlines for us the pattern of standing waves in the metal sheet. The standing waves automatically divide the length and width of a plane into an integral number of half wavelengths, as in figure 4. It is only then that a standing wave can be sustained. This is so by definition. Standing waves cannot exist unless they divide their medium into an integral number of half waves. A standing wave having a fractional wavelength cannot be sustained. We can also put it in another way. The dimensions of the plate are the factors that govern what is the size or wavelength of the standing wave that can be sustained in that plate. When a structure is in resonance, which means that it vibrates at a frequency that is natural to it and is most easily sustained by it, it implies the presence of a standing wave. Let us see if we can visualize this kind of behavior in 3 dimensions. We could take a transparent box, as in figure 5, fill it with a fluid, and disperse particles in it with the same specific gravity as the fluid so that they stay dispersed in the fluid and do not sink to the bottom. Then, by vibrating the walls of this box from all 6 sides in a synchronous manner, we could cause these particles to aggregate in a symmetrical 3 dimensional pattern. This pattern will look like a highly enlarged crystal if we assume that the aggregated lumps are analogous to atoms in a crystal. We have again produced a standing wave pattern in this box, which is a 3 dimensional analog of the standing wave in the string and the metal plate. At the same time, we have produced a 3 dimensional object analogous to a basic building block in nature and a highly ordered crystal. And we have done this simply by applying sound to an amorphous, disorganized suspension of particles. In the box, we have set up an interference pattern of standing waves, which we will soon explain, that governs the position of particles. In short, by using sound, we have introduced order where previously there was none. It may occur to us that a crystalline structure may be seen as representing sound interacting in a volume. Is it possible that the orderly pattern of atoms in matter is the result of the interaction of some kind of sound waves and chords in matter? Superposed sounds. Now let us go one step beyond and see whether sound can also be used for storing information or knowledge. A shallow round pan and 3 pebbles are all we need for this experiment. Fill the pan with water. Now drop in 3 pebbles simultaneously as shown in figure 6 and watch the ripples spread in the pan. Each pebble is the source of the waves spreading evenly across the pan. Let us neglect the wavelets reflected back from the walls of the pan. These waves cross each other and create quite a complex pattern of wavelets on the surface of water. They look pretty chaotic to us. There is, however, an order in this apparent chaos. All that has happened is that the wave produced by each individual pebble expanded and reached the edge of the pan. In so doing, the waves have crossed and interacted with each other on the way to the edge of the pan. This interaction created a complex pattern that is called an interference pattern. If we carefully analyze this pattern, however, we can trace back each wavelet to its source, the pebble. Let us now quick freeze the surface of the water in the pan and lift out the resulting rippled sheet of ice. We are holding in our hands a record of the interference pattern of waves, or we may even call it a hologram. Interference patterns and beat frequencies. In order to clarify what an interference pattern is, we have to learn 2 additional properties of sound in its different forms. 1. Constructive and destructive interference, and 2. Beat frequencies. Let us take the first one. In figure 7a, you will see what happens when 2 wave patterns of identical frequency and amplitude or wavelength meet. Let's try to superimpose them on each other. In figure 7a, we see that the hills and valleys of the frequencies in rows A and B match each other. If we superimpose them by measuring their heights or amplitudes from their respective baselines, then we find that the hill matches hill, valley matches valley. And when added up, they produce a waveform twice the height of the original waveforms as shown in row C. This is known as a constructive interference because it builds up the amplitude. If we now look at figure 7b, we find that hills match valleys and valleys match hills. And if we add them up, we shall find that they cancel each other out, as the flat line in the row C indicates. This is known as a destructive interference. This is what is happening in a pan of water. If we look at the ripples in the ice sheet, we shall find that where hill meets hill, we end up with a hill double the original wave height. And where hill meets valley, we find just a flat spot. This is the nature of an interference pattern. However, many forms of interference patterns are possible. We may have them in a single dimension, as when we vibrate a string, or in 2 dimensions, as in our flat pan, or in 3 dimensions, as in our box in figure 5. Beat frequencies. Now that we know that what an interference pattern is, it will be relatively easy to understand a beat frequency. In figure 7c, we see a frequency in row A, let's say it is 50 cycles per second, and a frequency in row B, which let's say is 60 cycles per second. If we add them up as we did before, we shall discover an interesting phenomenon. Row C shows the result of adding the two frequencies. What we see is a pearl-shaped waveform superimposed on top of our A and B waveforms. The reason for this becomes obvious if we examine figure 7c carefully. Starting from the left, we see that in row C, the amplitude, wave height, is low where the hills and valleys approach each other, and high where the both waveforms coincide and reinforce each other, which results in constructive interference. The wave patterns are said then to be in phase, to use a technical term. Now, as we move to the right, we notice that the A and B waves gradually go out of phase, and the hills start facing the valleys, thus opposing each other, which means that a destructive interference is occurring. This destructive interference reaches its maximum in every fifth cycle, forming a narrow waist in the amplitude or volume of the sound at those points. The Pearly pattern in row C will therefore be a modulation of the basic sound, which has a fixed amplitude. Modulation means a change that is being caused in an otherwise smooth or even behavior. In our case, it means an increase and decrease in the amplitude or volume of the 60 and 50 cycle per second sound. This modulation will occur 10 times per second with minima occurring every 6 cycles. This 10Hz modulation is called a beat frequency and is the difference between the A and B frequencies, or 60 Hz minus 50 Hz equals 10 Hz. Were we to make a 10 cycles per second sound and B a 12 cycles per second sound, we would then have a 12 minus 10, 2 cycles per second beat frequencies superimposed on those two basic frequencies. The knowledge of these two properties of sound will be important toward the end of this book. Note that the difference between the two fast frequencies produces a third frequency that is much slower than the first two. This, then, is a beautiful device for converting high frequencies to low ones. Nature's information storage. Let's go back now to the sheet of ice we lifted from the pan and find a proper light source to illuminate, as in figure 8. We shall find to our great surprise that we can see the 3 pebbles suspended in mid-air if we look through the ice toward the light. This will look very three-dimensional to us. This is a totally unexpected result. It seems that the rippled surface of ice or the interference pattern has somehow stored the information about the whereabouts and the shape of the pebbles. The ice surface acted as a distorted lens in such a way as to focus the light to the points taken up by the pebbles that have caused all these ripples. The chaotic looking ice surface is actually an information storage device. Suppose now that due to a momentary gap in attention or plain clumsiness, this ice sheet slips out of our hands, drops on the floor and breaks. We sadly collect the pieces, but before throwing them all out, we hold up one of them and eliminate it the same way as we did the last sheet. To our great surprise, we find the 3 pebbles again projected in mid-air, as in figure 9a. But how come? You may remember that the information about the whereabouts of each pebble was carried by the waves moving to the edge of the pan. We know if we drop just a single pebble into the pan, it would be very easy for us to locate it. We would simply seek out the center of the concentric wave rings or wave fronts. We know also that the waves from each pebble cross the face of the whole pan. Naturally, they must have interacted with each other across the whole surface of the pan on every square centimeter of its surface. We can show it like this. The arcs created by each pebble are crossing a small piece of the surface, and each arc can be traced back to its origin, as in figure 9b. This is the basic principle of the hologram. However, I would not recommend that you actually try to perform the experiment just described. It will not work in practice for certain complicated technical reasons which we shall bypass, but it is perfectly useful for the purpose of explaining the workings of the most exciting information storage device, the hologram. It is nature's way of storing information. There is already evidence that our brains store information in a holographic form. This kind of storage device is the most compact known in nature. An example of this is the genetic code carried in our chromosomes. Each cell in our bodies carries all the information required to make an additional copy of our bodies. Our success in storing information in the system just described depends naturally on the predictable and orderly behavior of the waves in the pan. They must be consistent both in velocity and distance between the waves or wavelengths. This is what makes them reliable as carriers of information. Otherwise, all we would get is a hodgepodge of waves. Here is where coherency comes in. Coherency. It would be good at this point to describe the way a real hologram is made so that you become familiar with its important concept. By coherency, we mean an order of a certain kind. In this case, we shall talk about coherent light, without which a good hologram cannot be made. The most popular source of coherent light is a laser. The first important aspect of laser light is that it produces light of a single frequency. We all know that our sun sends us light that can be broken down by a prism into a spectrum containing all the colors of the rainbow. A laser produces light of just a single color from the rainbow, which we call monochromatic light. In addition, the light emitted by the laser is coherent or goes in step, by what we mean that all the light coming out of the source is moving forward in even, flat fronts, as in figure 10. This makes it possible for the laser light to stay in a narrow beam over very large distances. There is a better way to describe coherency. Suppose we have a parade and a company of soldiers marching in military fashion down a main street. They are moving along, 10 abreast, very carefully aligned in each row. The distances between the rows are fixed, which is analogous to the even distances between the crests of the light waves. That they are carefully aligned abreast, none of them is sticking out of the line, is analogous to the light being in phase or in step. In short, the row of soldiers is analogous to the light emitted by the laser beam. Suppose now that a slip-up occurs, and one of the soldiers, not watching his fellows, shifts out of his row, moves forward, and steps on the heel of the fellow in front of him. The latter panics, thinking that he is lagging behind, and he jumps forward and bumps into the fellow ahead of him. Now this starts a general panic in which soldiers bumping into each other disrupts the nice even width of the moving column. The neat column diverges, broadens, then opens up completely in great disorder, in spite of the fact that their commander is blowing his whistle, tearing at his hair, and using strong language to get his men back into line. What we have learned from this disastrous parade is that a beam of light can stay in a narrow beam similar to a laser's beam only as long as it is coherent. When coherency is lost, the beam will tend to expand rapidly, just as will the beam of regular flashlight. The hologram. We have seen before that information can be stored by an interference pattern of waves. To have interference, we must have at least two interacting components, and here is how it is done as shown in figure 11. The laser light beam is split into two components by a half mirror, that is, a semi-transparent mirror. This allows part of the beam to continue undisturbed while part of it is deflected to another mirror. Both narrow beams are spread open by lens. The upper beam, which we shall call the reference beam, arrives at a photographic plate after an eventless flight, since no event of note has occurred on its way to the plate. It proceeds then to deposit its imprint on the film. The other half of the beam we shall call the working beam. This beam strip had an event. It had encountered on its way an object, which in this case an apple, that it had illuminated and with which it had interacted. We don't consider encounters through mirrors and lenses as worthwhile talking about. The working beam will then be reflected from the apple and fall on the film. There it will meet its twin, the reference beam, and will tell it all about its experiences with the apple. Neither of them suspect that their interaction is being recorded on film. The interaction between the two beams will cause ripples to form between them, which will form the interference pattern we already are familiar with, since the light waves will behave in this case the same way do water waves. However, these ripples do not at all resemble the shape of the apple, but as we already know, the ripples in the photographic emulsion do contain information, and that information can be elicited from the film by illuminating the exposed film with the same light used in making the hologram. As we do that, we shall see that the apple appears suspended in mid-air and looking very three-dimensional and real. We could be easily deceived when viewing an image reconstructed from an hologram that we were seeing the actual object. Note that the important part of the holographic image making is interaction of a reference beam, a beam that is pure, virgin, and untouched, with a working beam, which has had some experiences in its life. The magnitude of these experiences is being measured against a reference beam, which serves as a baseline for comparison. Our whole reality is constructed by constantly making such comparisons. Our senses, which describe our reality to us, are making these comparisons all the time. Unfortunately, our senses, having no absolute reference line, must generate their own relative reference line. But whenever we perceive something, we always perceive differences only. It would be useful to take one example from nature to see how much differences are put to use in a very obvious way. Take the bat, for instance. We all know that this little mouse like fellow lives on insects he catches in flight. Since he is active at night, he has developed a sonar like device that serves him very well and enables him to make a reasonably easy living. He has highly specialized structures in his head that allow him to emit a very high frequency sound and to direct it in a fairly narrow beam. This is his reference beam. As his beam encounters a flying insect, some of this sound will be reflected back to the bat, as in figure 12. He picks up this echo, or we can call it the working beam, and compares it to the original squeak or chirp. There will be a difference between the two called the Doppler effect, and this difference tells the bat how far away the insect is and how fast it is flying relative to him. As the bat successfully closes in on the insect, the difference between the two frequencies, the emitted frequency and the echo, diminishes. When it becomes very small, the bat opens its mouth and swallows the echo. Some echoes, as the bat surely knows, are tastier than others. We see now that by appreciating the difference between the two sounds or vibrations, one can get along quite well in life. There are many creatures that make a living by appreciating differences in sound: porpoises, whales, and many others. We humans also utilize this technique in less obvious ways in color, vision, hearing, etc. Oscillators and resonant systems. We may describe an oscillator as an object that moves in a regular, periodic manner. We may call a vibrating string an oscillator, or a weight hanging from a spring or a pendulum, anything that performs a repetitive, periodic movement, that is, vibrates. We may generalize and say that oscillators produce a sound or a note, whether audible or not, as long as they alter the environment in a periodic manner. That environment may be tissue, as in the heart aorta oscillating system, water, air, electrical fields, gravitational fields, or anything else. Suppose we tune two violins, then put one of them on table and play a note on the other. If we watch carefully, we shall see that the same string that we are playing on one violin is also humming on the violin that we placed on the table. Clearly, there is a sympathetic resonance on the course between the two. Let us analyze what is happening. When we draw the bow over the string, it vibrates at its own natural frequency, which we call a self frequency. Since the two violins are correctly tuned, we know that the natural frequencies of both strings were identical. Within a system like this, we shall call the two violins a system, it is very easy to transfer energy. In this case, we are talking about acoustical energy. The airwaves generated by the first violin impinge on the second violin. The string that is tuned to the emitted note will absorb the energy of the waves of that frequency preferentially, because that energy comes to it at its own natural frequency. The energy transfer within this system is therefore optimum, and such a system, made up of two tuned oscillators, is called a resonant system. Let us take another example. Suppose we get several old-fashioned pendulum-type grandfather clocks. Let us hang them on a wall and arrange their pendulums so that they will start out beating each at a different angle that is out of phase with each other. In a day or two, we shall find that all the pendulums are beating in phase, as if locked together. Pendulum length should be the same for all of them, by the way. Here we see that the tiny amount of energy that was transmitted through the wall from clock to clock was sufficient to bring them into phase with each other. If we disturb one of the clocks, it will get locked into rhythm quite fast. The larger the number of oscillators within such a system, the more stable the system and the more difficult it is to disturb. It will force a wayward oscillator back into line very quickly. The sound of the body. The heart is a big noisemaker. We can easily check this by putting our ear on someone's chest and listening to it. Its beat shakes the whole body, and the body has a typical response to this beat, which is quite easily measured. Figure 13 shows what such motion looks like when measured with a sensitive seismograph-like instrument. This movement is clearly related to the heartbeat. In fact, the largest peak we see in the graph is caused by the ejection of blood from the heart's left ventricle. The portion between the large peaks looks fairly irregular and is caused by the vibration of the body due to the action of the blood in the aorta, which is the largest artery in our body. This irregular portion is due to a destructive interference pattern set up in the aorta, as will be shown later. When we stop breathing, the irregular signal in the figure 13 turns into a nice, regular, practically sine wave pattern. Figure 14. This is surprising, and when we look into the reasons for this behavior, we find that the heart aorta system has become a so-called resonant system, as shown in figure 15, in which the length of the aorta forms one half a wavelength of this system. By resonant systems, we mean that it resonates just like a tuned musical instrument. Here is what seems to be the case. When the left ventricle of the heart ejects blood, the aorta, being elastic, balloons out just beyond the valve and causes a pressure pulse to travel down along the aorta, as in figure 16. When the pressure pulse reaches the bifurcation in the lower abdomen, which is where the aorta forks in two to go into the legs, part of the pressure pulse rebounds and starts traveling up the aorta. If in the meantime the heart rejects more blood and a new pressure pulse is traveling down, these two pressure fronts will eventually collide somewhere along the aorta and produce an interference pattern. This is reflected in the movement of the body and is the reason for the irregular pattern of the body motion in figure 13. However, when the breathing stops, it looks as if some communication has been set up between the heart and the bifurcation. Some kind of signal seems to travel from the bifurcation to the heart, saying it to heart, hold it. Hold your next pulse until the echo from the bifurcation returns to you. Only then should you eject the next quantity of blood. When this happens, and the echo and pulse move out of the heart together, and they continue to move up and down in synchrony, then such a system is said to be in resonance. It causes the body to move harmoniously up and down about 7 times a second, hence the nice, regular, large amplitude sine wave pattern in figure 14. The amplitude or height of this signal is about 3 times the average of the normal signal. Another characteristic of resonant behavior is that it requires for its sustenance a minimum amount of energy. Well, but how long can we hold our breath? Certainly not over a minute or so comfortably, and so we start breathing and ruin the nice rhythmic pattern. Let us not forget now that our body includes our head, and inside the skull, carefully packaged, is a very delicate instrument, the brain. This brain is cushioned by a thin layer of fluid and is wrapped in a tight bag, the dura. About the simplest way to visualize this system is to have a relatively soft, round fruit, such as a peach, enclosed in a can containing a heavy syrup. If we shake the can, we find that the peach will hit the top and bottom of the can and be accelerated with a small delay in the direction in which the can is moving. This movement is quite small, only 0.005 to 0.01 millimeter. This is exactly what happens to the brain. The question is, how come we are not aware of this happening to us? It's probably because when something is happening to the nervous system for an extended period of time, and that event is not traumatic, it will not be brought to our conscious attention. Because the portion of the brain that is in charge of censoring and separating meaningful signals from unmeaningful ones will relegate it to the heap of unimportant signals, which require no conscious processing. We know from experience that we can easily get used to and disregard the loud ticking of a clock next to us or the noise in the cabin of an airplane. The noise is, however, filed away somewhere and affects us in some subtle ways. If we were to ask the brain how it would like to be treated, whether shaken at a random, irregular rate or in a rhythmic, harmonious fashion, we can be sure that the brain, or for that matter the whole body, would prefer the latter. Rhythm entrainment. Suppose we go out on a balmy summer evening and notice some fireflies settling in a bush, blinking off and on. At first, this blinking is random, but fairly soon we notice that an order is slowly developing. After a while, we see that the fireflies in the whole bush are blinking on and off in unison. This phenomenon is called rhythm entrainment. It seems that nature finds it more economical in terms of energy to have periodic events that are close enough in frequency to occur in phase or in step with each other. That is the meaning of rhythm entrainment. Let us take another example. When electronic circuits are built so that they contain oscillators of electronic type common in radio or TV circuits that happen to oscillate in frequencies that are close enough to each other, there will be a tendency of the oscillators to get locked in step with each other and oscillate at the frequency of one of them. Usually it is the fastest oscillator that will force the slower ones to operate at this pace. Here again, nature feels that it is more economical if two or any number of oscillators that vibrate at frequencies close enough to each other work together rather than insist on keeping their small differences. Major effects of rhythm entrainment occur in nature. Our biological rhythms are entrained by light and to a certain extent by gravitational effects. These are the two most obvious factors. However, magnetic, electromagnetic, atmospheric, and subtle geophysical effects influence us in ways that are not presently well understood. We usually get up with daylight and go to sleep at night. The sleep wake cycles of animals and birds are more strongly tied to the light dark cycle than those of our civilized, and of course, humanity, because we have developed artificial sources of light and can change our light dark cycle at will. However, we all know that when our light dark cycle, which runs our biological clocks, is drastically altered, as when we take long jet flights in an east west direction and cross several time zones, such an interference with our biorhythm has quite a marked effect on our ability to function in the new environment for a day or two. An interesting experiment was performed by Professor Frank Brown Jr. of Northwestern University, Evanston, Illinois. In order to check out what factors influence the biorhythm of animals, he had some live oysters shipped to his lab from the Long Island Sound, a distance of about 1,000 miles in east-west direction. These oysters open and close their valve in rhythm with the tides. The animals were shipped in tight opaque containers filled with sea water. Upon arrival, they were stored in a lab with no natural daylight. On first examination, the oysters, geared to the rhythm of tides in Long Island Sound, kept opening and closing their valves. In about 2 weeks, they started shifting their rhythm, and a while later, they stabilized in a rhythm that coincided with the passage of the moon over Evanston, Illinois. In this case, we may assume that the oysters are indeed rhythm entrained by the gravitational effects of the moon. However, it is not only we, the tiny creatures of this planet, who are rhythm entrained. The big and mighty asteroids and the planets themselves are rhythm entrained and develop resonances in their orbits as they rotate about the sun. Asteroids, which are minor planets, will not only respond to the gravitational pull of the sun, but will also be strongly affected by the gravitational fields of the major planets. They must dance, so to speak, to the tune of two masters, and so the asteroids develop little dances to the music of the spheres in which they pay tribute to the forces involved. They go into resonant orbits and describe minor loops around the planets within their major loop around the sun. All the phenomena described in this chapter are of a periodic, repetitive nature. We have made a generalization at the beginning, saying that when such a rhythmic movement occurs, it affects its environment, whether that environment is air, water, solids, electromagnetic, or gravitational fields. In the case of air, water, or a solid, these vibrations will affect our near environment only and can be called sound on the course. If we shake our electromagnetic or gravitational fields, the disturbance in the environment will travel faster and farther. We will still apply the word sound on the course to it, although it will be a sound of a different kind since it will travel at the velocity of light. We could actually associate our whole reality with sound of one kind or another because our reality is a vibratory reality and there is nothing static in it. Starting with the nucleus of an atom, which vibrates at enormous rates, the electrons and the molecules are all associated with characteristic vibratory rates. A most important aspect of matter is vibratory energy. When we think, our brains produce rhythmic electric currents. With their magnetic components, they spread out into space at the velocity of light, as do the electric waves or sounds produced by our hearts. They all mingle to form enormous interference patterns, spreading out and away from the planet. They are admittedly weak, but they are there. The more finely our systems are tuned, the clearer a signal we can pick out of the general noise and jumble of sounds on the course. When you have a system of tuned oscillators, even the tiniest signals can be picked up. You may recall that it requires very little energy of the correct frequency to drive a resonant system. Our planet itself is producing shock waves in the plasma that fills the solar system. These shock waves interact with those caused by other planets and produce resonances between the planets and the asteroids. In short, our whole reality is based on one common factor, and that is periodic change or sound. Our senses are geared to respond to all these different sounds on the course, but we are always comparing one sound with another. We can appreciate only the differences in sound. Summary. We have seen various ways of producing sound. We know that when a string or any other structure vibrates, it may develop standing waves. These are waves that occupy a fixed, on the course, position in any structure, whether it is a string, a plate, a container filled with a liquid, or a blood vessel. Nodes are the spots in which minimum motion occurs. When sets of waves are superposed, interference patterns result. A hologram is an interference pattern of light waves on a photographic plate. When two differing frequencies are superposed, beat frequencies result. Coherency is an in-step or in-phase behavior of waves. Oscillators are devices that move in a periodic, repetitive fashion between 2 points of rest. Our bodies are also such devices. Oscillators vibrating out of phase with each other may get locked into phase through rhythm entrainment. A system of oscillators that is in phase can resonate. Our reality is a vibratory reality filled by sounds of different kinds. We respond to differences in these sounds.